So we have what we call chapter 18, which is just thermodynamics and equilibrium. So this you learn from chapter 14, no, chapter 6 in your Gen Chem, and this is your chapter 14. Okay, so what we're going to do is we're going to combine what you have learned from those chapters. So if you are going to recall thermodynamics, I think you know what's the first law of thermodynamics. So if I'm not mistaken, this is the last chapter that you have in your Gen Chem 1. Okay? So the first law of thermodynamics is essentially the law of conservation of energy. So if you're going to recall your first law of thermodynamics, is just the internal energy is just the sum of the kinetic and potential energy of the particles that makes up the system. Okay, so usually you look at this change in internal energy as the internal energy in the final condition minus the internal energy in the initial condition. And you learn that the mu that we have there, that's just we could say energy. It is two forms. That's Q and W. I don't know if you recall what this means from your previous chapter. Okay, so usually it says there the exchanges of energy between the system and the surroundings are two types of uh, heat and work. So remember, you have the system, the one that you are interested to, and anything around the system is the surrounding. And usually there's an exchange between the matter and the energy between the system and the surrounding. And we're after the exchange in the energy that we have here. So what do we call with the system and the surrounding all together? What do we call them? You recall what's the term that we use that describes both the system and the surrounding? Anyone? It's just like you and I makes what? The universe. So the system together with the surrounding is known as what we call the universe. So if you're going to look at the internal energy that you have there, so it depends on two forms. You have the heat and you have what we call the work. Okay, so when we're talking about work here, it's the one that deals with what we call the gases. Okay, so usually when we have heat, it has something to do with if it goes inside or outside. Okay, so there's a system here, and this is what we call the surrounding. So the energy form that goes within or the energy that goes into the system and goes out of the system, usually that's what we call the heat. So there's an exchange there. So when heat is evolved by the system, so that means Q is negative. When heat is absorbed by the system, then that is positive. So what does it mean? If the system gain heat, you have a positive Q. If the system lose heat, then you have negative Q. So one will decrease the internal energy and the other one will increase the internal energy. It makes sense because you have this what formula. So if this becomes what? Positive, this goes up. If this becomes negative, this goes down. So those are the type of what? Multiple choice question that you're going to be asked. Okay? Now, as I've told you, that's it. Now, where do we get the work? Work has something to do here with gases. So work is just the negative of pressure times the change in volume. When the system expand, so what does it mean? You have a positive delta B. And if you have a positive delta B here, you multiply it with the negative, your W is what? Negative. Okay? So the system does work on the surroundings which decrease the internal energy. Remember, you have here delta U is equals to Q plus W. So if your W is negative, okay, your internal energy will decrease. And that's the time when the system does work on the surrounding. Now, there is also the time when the system contracts where your delta B is negative. So if you have negative times negative here will give you a positive W. And if it gives you a positive W, then you increase your internal energy. So the term that you have to worry about him, the system does work on the surrounding. Here, the surroundings does work on the system. So we could say the system works here. Or what? Work is done by the system. Here, work is done by the surroundings. The surroundings do work on the system, which increases the internal energy. Does this make sense? If you work, what happened? Do you feel energized? Or
Yes.
you feel what? Tired, right? So imagine you're the system. So if you do the work on the surroundings, you decrease your energy. So you become a little bit what? Tired, you lose energy. But if something do the work for you, okay, you become more energized. Okay? So maybe that's the aspect that you can what we call remember. So this is where you see, okay, how work is being done. So as you could see here, what's the delta B here? Okay, since BF is higher than BI, so you have a positive delta B. And if you have a positive delta B, your work is negative. Okay? Now, as you can see here, what we are talking about is just Q and what we call W. Because if I can remember, if anything that that you can recall from your Gen Chem 1, it has something to do with delta H. And we call delta H as what? The enthalpy. And you can connote delta H as just the Q at constant pressure. Okay? So what's the delta H that you know? You have the exo, you have the endo. And the best way for you to remember them, use the first two words, they're endo. So that means the energy enter the system. Exo, that means the energy exit the system. So I think that's the best way to what we call remember them. And the overall thing that you could recall that the internal energy that you have is just equals to what? Delta H minus P delta B. But if you're going to simplify it, this is just like this. That's where they came from. The energy, the internal energy is equals to heat and work. Okay? Now, what's the problem with the enthalpy. So enthalpy can just tell us what is happening to the system. Does it absorb heat or release heat? Okay? Now, they found out that some reaction happen what we call spontaneously. So, they want to find a way to determine, is there a way we can predict if a given reaction is going to be spontaneous? So before we go to answer that question, we have to recall now, what is this spontaneous process? Okay? Because they want to understand why a chemical reaction goes in a particular direction. Okay? So whenever you're given what? A spontaneous process, it's a physical or a chemical change that occurs by itself. Is that it does not require outside force, and if it continues until the equilibrium is reached. So for instance, what will I do? So if I have this pen, okay? So if I release it, what happened? It will fall spontaneously, right? Now, can I get the pen back? Let's say maybe if I'm a Jedi, I can use the force, but in reality, no such thing exists, right? So in that case, when the pen falls, that happens spontaneously. But if you want the pen to go back to my hand, okay, there's no such thing that exists. What you do is I have to intervene and I have to put it myself here. So that's the difference. This when the pen falls from my hand to the other hand, it happens spontaneously. But if I want it to go back to where it is, there's an outside intervention. So when you have a spontaneous process, it occurs by itself. It does not require outside force. Okay? So what classic example I can give you here? Before I go to what we call some classical example that is being discussed. Let's try to do it in our everyday life. What can you say about here? Is it a spontaneous process? Anyone? Is failing an exam a spontaneous process? I want everyone to answer that question. If you agree, thumbs up. Is failing an exam a spontaneous process? I remove the sharing thing so I can see who answers. Wow. What if I tell you that if failing an exam is a spontaneous process? Why? You don't do anything. What will happen to you? There is an exam. You don't do anything. What will happen to you? Ah. When you study, when you read your notes, when you attend your lecture, okay, wherein you are here, not that you just open it and then you went out, and then the lecture is already down, you're still logged in, okay, that's an outside intervention. And if it's an outside intervention, then it's not spontaneous. So you don't do anything. You take the exam, you fail. Because it happens spontaneously. There's no outside intervention like this one. Okay? Whatever I do, this pen will fall unless I have an outside intervention. So just take it as this. Okay, this pen is the exam. I want a carefree life. Who cares? There, the pen fails. There, the pen is the exam. There. You fail the exam. Did you get that?
Yeah.
Failing an exam is a spontaneous process because you don't do anything. So what will happen? That's the results. Okay? So right now we go to the classic example that we have. So if you have a ball on the hill, what will happen spontaneously? Okay? The ball will fall. The ball will roll. Now, can you expect the ball to go back to the hill or up of the hill? Of course, it's not. Okay. So whatever is spontaneous in one direction is non-spontaneous in the reverse reaction. Are we clear on that?
Understood.
That's what you get if you take the course with me. I don't know. I, I try to apply the things that we have in our class in your everyday life. Okay? At the end of this chapter, you will also learn the answer to the questions, are diamonds forever? Okay? So, anything that happens spontaneously in one direction is non-spontaneous in the reverse direction. When you put sugar in water, what will happen spontaneously? The sugar will
Dissolve.
dissolve. Okay? Now, how are you going to recover your sugar? Can you just tell the water, get out? I want my sugar back. You have to do something. Okay? When you don't do anything and a process happen on its own, that's a spontaneous process. That's why if you don't study for your exam, the spontaneous process there is, you're going to fail the exam. Okay? Now in the waterfalls, what will happen to the water? It's always water coming from up, going down. Have you seen the reverse happen on its own? Maybe if you have some mechanical machine or mechanical construction wherein the reverse happened, but that's already where the outside intervention, okay, is happening. Rusting, right? I don't know if you have a car or your family has a car. You know, corrosion is just started with a little what? Dot, and then all of a sudden all the place corroded. That's another spontaneous process. Now, some of the spontaneous process can happen fast, some can happen a little bit slow. And the only way for you to prevent them is what? Maybe to put some inhibitor to slow down the reaction or apply other outside intervention. Now, enthalpy cannot describe this thing. Why? Because when they look at some of the reaction, okay, some of them has what? Positive delta H, and some of them has a negative delta H. So delta H is not enough to determine whether you have a spontaneous reaction or not. Now you might say, what's the example here? Water at room temperature, what will happen? Or ice at room temperature, what will happen? Spontaneously, it will become water, right? So what's the delta H for that process? Is it positive or negative?
Positive.
Okay. You need heat so that your solid ice dissolves in water. It happens spontaneously. You put it in the room temperature. You have an ice, later on, it melts into water. Now you might say, Professor, how about the heat that is intervening it? You didn't put the heat there. It's always there. When you have ice, you put it in what we call a room temperature. It will always go to water. How are you going to prevent it? How are you going to prevent ice from becoming liquid water? You put it back in the freezer. But If you put it, let's say, at room temperature, that will happen spontaneously. So that's a positive H, delta H. Now, how about an example of what we call a negative the delta H? Anything that refers to burning, like your methane. If you react it with oxygen, you're going to produce CO2 plus 2H2O. And it usually gives you energy. Okay? So that's just example of what we call spontaneous reaction that has a positive delta H and a negative delta H. So positive delta H is not, I mean, the delta H is not enough to determine if a reaction will be spontaneous or not. So, okay, they apply a new quantity. They call it entropy. So the first law of thermodynamics cannot help us to determine whether a reaction is spontaneous as written. So they need another quantity. And it comes in the form of another letter E, right? Your enthalpy is E, your energy is E. I like it because my name starts also with letter E. Okay? So what do you to prevent the confusion? So if enthalpy is H, your entropy is letter S. So what is this entropy? Okay? So entropy is a thermodynamic quantity that is a measure of how dispersed the energy of a system is among the different possible ways that a system can contain energy. It's a little bit too deep. I tried to make it in a much simpler one. Delta S here, or S, is just a measure of randomness. It's still hard for you, then I would say it's a measure of disorderliness or disorder. Okay? So that is what we call entropy. Now, what did they observe? Most of the spontaneous reactions are what? They become more ordered or more disordered. I'm going to go back here in the reactions that we have. Most, if not all, of the reaction or spontaneous reaction, what do they observe? From solid going to liquid, did it become more ordered or more disordered?
More disordered.
Okay? All becomes more disordered. Look around the world. Which is easier? To have order or disorder?
Disorder.
It's more disordered, right? That's why I think why in 2016 a guy who promised I'll bring order won the election. And what happened? It just happened that he's more disordered on his own. He's more what we call chaotic on its own. Okay? But if you're going to look around that, it takes effort for a system to be in order compared to one what we call disorder. Try to remember your childhood. Okay? Why do you get time out? Because that's what I do to my children. Hmm? It's easier for the kid to be what? To just put mess around all the toys. Like my daughter here. When I went back home yesterday, it's all mess. Okay? Now for her to bring back the toys in order, you have to intervene. Or he had to do it himself, put order, right? So it takes energy to have a system to be in order. For a system to be disordered, it will happen on its own. So that's what we call spontaneously. Okay? the system will become more disordered. So solid becoming what? Liquid. So this is more disordered compared to this one. Am I right? Because solid is arranged in its own what we call the lattice. Okay. Liquid is a little bit more disordered. That's why solid has what? Definite shape, definite volume. For the liquid, it's just definite volume, but not definite shape. Okay? So if we're going to look at the entropy, if this entry here is just so hard for you to understand, the measure of how dispersed the energy of a system is among the different possible ways that the system can contain energy, we could just say measure of randomness or disorderliness. And try to look at this as this way. What will happen here? If you have two bulbs, one bulb has what we call the gas, the other one is empty. If you open it, what will happen?
The gas will disperse.
Okay, it will go there. Can it happen? Spontaneously. Okay. Now, how are you going to put this back going there? Because usually if you open this one, this is what will happen. But for this to be back there, you have to put some effort. You have to do some intervention. But what you have here, if you look at in terms of an energy, okay, since you open this one, the kinetic energy is spread out, so the entropy of the system increase. So here, this is what? More ordered because you put them here. But this is more disordered because it's already on the both sides of the what we call the evacuated bulbs. Okay? And also try to think of it, if you have a pendulum, what will happen to the pendulum? You try to move it like that. It keeps moving, right? And then sometimes there, when it stops, okay, the energy is already dispersed there in your what we call pendulum. I think I have it on my later slide. Okay, so what they introduce here, since the first law of thermodynamics cannot predict the entropy, they introduce the second law of thermodynamics, and it has something to do with this statement: the total entropy of a system and its surrounding always increases for a spontaneous process. So what does it mean? When you have a system or a spontaneous system, you expect it to become more disordered. Okay? So this is the note that you need to remember. Entropy is a measure of energy dispersal, not a measure of energy itself. Delta H is a measure of energy, but delta S is not. Okay? It's usually like the way that they look at it is measure of energy dispersal. So it has something to do with the energy with a given time. So not time, temperature. My bad. So that's one of the difference of this what we call entropy from enthalpy. Enthalpy, if you're going to look at this, they're always what? In joules. But your delta S is always joules per degree Celsius. It's a measure of the energy dispersal. Okay? So for a spontaneous reaction or process at a constant temperature, we can state that the second law of thermodynamics in terms only of the system. So delta S is equals to the entropy created plus Q over T. What is Q? Anyone? What is
Quantity.
Q? That is the heat. We have discussed this earlier. Q is heat. Okay? And they said for a spontaneous process, usually the delta S is higher than Q over T. So that's the thing that they look at this, what we call second law of thermodynamics. So the way that we could put it here, let's say the pendulum is put in motion, so all of the molecules moving in the same direction as shown here. So if it's moving there, okay, the molecules will also move. As it moves, the pendulum collides with other air molecules. When it comes to rest, in figure C, the pendulum has dispersed its energy. So this is a spontaneous process. Will the pendulum will go on like this forever? Even if you have that what grandfather clock or whatever they call that thing, okay, there will come a time that will stop. So if you're going to look at this, let's go at the reverse. Is this spontaneous?
No.
Okay. So this what happened. Consider the reverse process. It's not spontaneous. While this process doesn't violate the first law, it's going to violate the second law of thermodynamics because the dispersed energy becomes more concentrated as the molecules move together. So we could say delta S is just something to do with disorderliness. The more disordered the system is, the higher or the more positive is the delta S. Okay. So entropy is essentially related to energy dispersal. The entropy of a molecular system may be concentrated in a few energy states and later dispersed among many more energy states. And in that case, the energy of such system increases. So let's say before I go to this ice melting, when you have this what we call cup of coffee, okay? As the heat moves from your hot coffee, the molecular motions becomes more disordered. And in becoming more disordered, the energy becomes more dispersed. So you just disperse the energy. Okay? So when the ice melts, the molecules become more disordered, again dispersing the energy more widely. Now, when one molecule decomposes to give two, as in N2O4 producing 2NO2, more disorder is created because the two molecules produced can move independently of each other. I don't know in your own life, when are you productive? When you're alone or when you work with another person or when you work with a group,
Alone?
right? Because it becomes a little bit what? Disordered. If you're alone, I am alone and I am the order. Sometimes in the group, when I lead the group, okay, I'll take care of it. And then when I go back, okay, say something about it. That's what I do right now with some of the faculty there at PACE. Sometimes I'll just say, okay, I'll try to do what will happen, and then I'm just going to give the latest document and then put your input. Oh, it depends. Why? If it's your crush, you become more productive. Okay, but that's the thing in the nature. They said the more people that are involved, the more complex the works become. Or as a Facebook status says, it's complicated. Okay, it becomes more complicated when more people got involved. So that's the concept of this, what we call disorderliness, because chaos will be the spontaneous process for everything. The system will become more chaotic. That's what it means when we say more disordered. But that's the nature, okay, of the system. And if you're going to, and if you watch, because during that time I was able to read this Jurassic part, okay, chaos itself will find a way. Because what happened in the Jurassic part there, they make I think the genes where they put the DNA of the dinosaur, all, I'm not sure if it's all male or all female. And then what happened is they were able to procreate themselves. Okay, even if they just have one sex thing there. So if you're going to look at entropy for a phase transition, okay, so usually the system is this. In a phase transition process that occurs very close to equilibrium, heat is very slowly absorbed or evolved. And under these conditions, no significant new entropy is created. And this is the concept that you can apply for melting or for vaporization, where you use the heat of fusion or heat of vaporization as heat. You're going to have some problem on that. Okay? And we can also look at the entropy change like this one. Acetone is a volatile liquid solvent. It is used in nail polish. So the standard enthalpy of formation of the liquid is 247.6, negative 247.6 at 25 degrees Celsius. The same quantity for vapor is negative 2.16.6. Now you are asked what is the entropy change when 1 mole of liquid acetone vaporizes at 25 degrees Celsius. So maybe if you have problem like this, the thing that you're going to do is write your acetone. So this is what? Liquid and then acetone. And then we can put the delta H there because that's the one that is given. Okay. So in the liquid, you have negative 247.6. In the vapor, you have 216.6. And you have only what? In terms of the number of moles, all of them are 1. Okay. So if you're going to what we call do this thing for the delta H is equals to the summation of the delta H of the products minus the summation of the delta H of the reactants, right? So we're going to put there, what's the number? Negative 216.6 minus, because you just multiply everything by 1. What does 1? That's 1 mole. So 1 times negative 2.16 minus 1 times negative 247.6. So what do you get? Anyone? What's the number that you will get?
464.2.
Is it 464.2? If we were going to do it, this will become what? Negative 216.6 minus negative 247.6. So that will give you
31.
I get 31.
Yeah.
Now, the question that I'll ask you, is this valid? Is this a valid number? What does the positive 31 means if you're going to interpret it here? Remember, that's delta H. So a positive 31 means here you need 31 kilojoules for your liquid acetone to become gas acetone. Does that make sense? You're going to need energy for the liquid to become gas.
Yeah.
Okay. So that's the thing that you need to look at the numbers that you will get. Oh, you will say it's a transition from liquid to gas. So that means your delta H should be positive. Now the question now is, what could be the delta S in terms of sign? Will it be a positive or it will be a negative? Because usually, what did I say? Your delta S is positive, it is more disordered. And then your delta S can be negative, it is more ordered. So what do you think is the delta S for this system? How are you going to predict it? Will it be positive or negative? Anyone? Prediction only. Okay? So did you become more ordered or more disordered? What happened to the system? Did it become more ordered or more disordered? Okay, it becomes more disordered. So most likely, your delta S will be a positive. Now, how are we going to use that? So if you're going to look at this Q that we have here, that's the delta H that we're going to use. That's the value that we're going to use there. So we have the 31, that's a kilojoule. So we could say that's 10 to the 3 joules. And then you divide it with 25, convert this to what? Kelvin. So you have there 298K. So what do you get? You're going to get 104. And it is a positive. Because that means there, your delta S is a positive because you become more disordered. Question so far?
No.
So what are the criteria that they have for this spontaneous reaction? So the criteria that they have there is that entropy of the system and its surrounding must increase. So what does it mean? The entropy that you get is always higher than Q over T. It's always higher than the delta H divided by temperature. Then if you're going to realign this one, you will have it here, cross multiply, the temperature times delta S is always higher than delta H. So the way that they look at it, okay, so if you rearrange this one here, what will happen? You're going to move this on this side, so you have it like this. Wherein it's less than 0. Okay? Or if you put it in this scene, the delta H minus T times delta S is less than what we call 0. And later on, you will see that another quantity came out here that refers to whether a given reaction is spontaneous or not. Okay, we will go on that as we move on, because right now we already have the second law of thermodynamics. I want you to introduce to this one. So third law of thermodynamics is still in one way or another related to entropy. So in the third law of thermodynamics, they say here a substance that is perfectly crystalline at 0 Kelvin has an entropy of 0. So what does it mean? What usually happen at 0 Kelvin? You expect it to be solid, and in addition to that, you expect no vibrations that you have there. Because even if you're solid, there's still some movement of the atoms within the molecules. But at 0 Kelvin, stop. So you have here an entropy that is equals to 0. So what does it mean? As the temperature increases, the entropy also increases. Okay, the standard entropy of a substance, or its absolute entropy, this is the entropy value for the standard state of the species. So the same thing as you have like this one, that's the standard enthalpy. That's what you have when you have a standard state, 1 atmosphere pressure, okay, and 1 molar solution if you have it in terms of what we call solution. And they have a table for the value that they have, but you don't need to memorize them. But I want you to look at the table, even though they are the same substance, but different state. Look at the value that they have. I want you to look here. Does this value make sense? The bromine gas has a higher entropy compared to the liquid bromine. Does that make sense with what you understand so far about entropy?
The higher disorder.
Okay. So the higher the entropy, the more disordered it is. And I don't know if you're going to agree with me, but a gas is more disordered than a liquid. And a liquid is more disordered than a solid. So this is what we call the value that you have. You're going to use this value. I'm not sure if we can do it today or if ever next week to explain if indeed the diamond that you know is indeed forever. Okay? Too bad Valentine's Day is gone. And if you're going to look at some other values that you have here, so you have also the iodine here, but it's just solid. They didn't put the liquid and the gas. Okay? Or maybe we can recall the monoclinic and the rhombic thing here. They're almost what? Close to one another. Why? Anyone? Why do you think the value of this sulfur monoclinic and rhombic, which we have discussed, is just differed in the crystal structure? Why do you think the value that is close? Because they are both
Solid.
solid. Yeah. If you're going to look at this, what we call the entropy as graph with changing temperature, this is what you get. As the temperature increases, the entropy also increases. Why? What does temperature do to a particular substance? And you come to the point here. What do you think this is called? Anyone? If you're going to recall your chapter 11, this is your what? This part here, what do you call that? What do you call this? This is your melting point. And look at the entropy. Does that make sense that they have an abrupt change on that temperature? Is this what we call data here consistent to what it should be? Because what will happen? You start all solids and then after that all liquids. So the entropy that they have there is so much different from the entropy here going right to that value. And it's much worse when you go here from the entropy here going to that one because the system become more disordered. Everybody got that?
Yeah, understood.
So another thing that you need to remember, entropy change for a reaction. So entropy usually increases in three situations. A reaction in which a molecule is broken into two or more smaller molecules. And then a reaction in which there is an increase in the number of moles of a gas, and a process in which a solid changes to a liquid or gas, or a liquid changes to a gas. So those are situations wherein your entropy will change. So maybe let's try to work on this one. What could be the delta S sign there? Will it be positive or negative? I think I put the answer there.
Positive.
So if you're going to look at why it becomes positive, so you have here initially a solid, okay? 3 moles of solids of the reactants, and then they produce what? 13 moles of products. I don't know if you believe the saying, your single life was really happy, and then you got married, and then you got kids, and it just got more disordered. Come think of it, oh, it becomes more as all this. At least there's a positive thing on that. The entropy is positive. Okay? Because the saying that they have right now is not all positives are good news, right? If you got a positive COVID test, I don't think it's a good news. Okay? Now, the way that you compute for your delta S is the same as your delta H, wherein you have what? The delta S is just equals to the summation of the standard enthalpy of the product minus, okay, the summation of all the delta S of the reactants. So N there is moles. So let's try to work on this. When wine is exposed to air in the presence of certain bacteria, the ethanol is exposed to acetic acid, giving vinegar. So calculate the entropy change at 25 degrees Celsius for the following similar reaction. So if you are a Christian and you're going to have Holy Week next week, or you practice this so-called Holy Week, I think this is a great example. From the Last Supper to the cross, right? Because the Last Supper, they drank wine, and then when Jesus was in the cross, I'm thirsty, and he was given what? Vinegar. But based on the reaction alone, what can you say about the delta S before we calculate for the number of the delta S? Is it positive or negative delta S? Huh?
It's negative.
Negative. How about the others? So liquid, liquid, gas, liquid. So that alone you could say, oh, most likely it's negative. So here, when you say back up your statement, so you have to provide evidence, and the evidence that you're going to use is this one. So all of them are what? 1 moles, and all you need to do is put them in place here. So this is 161, 205, and this is what? 160, and this is 69.9. So try to calculate it. I just have to attend to my daughter who's here. So try to calculate the numbers. Get out, get out, get out, get out, get out, get out. Okay, get out, get out, get out, get out. I'm not done yet. Go, go, go. Why did you turn it on? Sorry for that. Sorry for that interruption. So all of them are here because their school is, I don't know, they have cases there, so they have 24 hours cleaning. Okay, so what's the number that you get? So if you're going to calculate it, it's the number that you get here, the sum for that, minus the number that you get there. And your number is what? What did you get? What did you get? All of you are commenting on my. What did you get? How many joules per Kelvin? Because this is J over K. So 160 plus 69.9 joules per K minus 205 plus 161. And your delta S is equals to what? Negative 136.1 or 136. So this back up your claim that should be negative. The reaction will become more ordered. Okay? So question so far with delta S. Because the next thing that we're going to do is about what is that physical quantity that we can use to determine if a given reaction is going to be spontaneous or not. Remember, the delta H will just tell us about what? If it's endothermic or exothermic. And then the delta S would tell us if it's more ordered or more disordered. But we don't have a physical quantity yet that tells us whether a system is spontaneous or not. What they said, spontaneous reaction can either be delta H or positive delta H or negative delta H. They also observed that if you have spontaneous reaction, the delta S seems to be more disordered. Okay, but there's no direct physical quantity that describes entropy, and it's just a combination of these two. The one that I have earlier here, that I said we will continue. So if we're going to continue that, you're going to get a physical quantity, and this is this one. Free energy. I don't know if you know this, what we call about Gibbs. I'm trying to find something that became popular before, but I cannot find it at this time. Maybe next meeting, about the guy. It's an entry in the book, and the entry itself is not really good. Okay, that's why usually whenever they ask, "What's the worst chemistry course that you have taken?" For me, I would say it's PChem. Okay, I can survive what we call organic chemistry, but PChem is another world, and that's one of the things that you discussed there. From J. Willard Gibbs, he introduced the concept of free energy. So again, you have a letter E, but they put it in terms of G. I think like this. In other book, they put it Gibbs free energy. And Gibbs free energy is what you come when you combine the enthalpy and temperature with entropy. Okay, so if you're going to come it with this thing, you can come up with that one. A change in Gibbs free energy is equal to change in enthalpy minus T uh, times delta S, or you can have it in terms of standard free energy change. Uh, Standard Gibbs free energy equals to standard enthalpy minus temperature times change in standard entropy. There are a lot of equations that you have here, and I call this the granddaddy equation, because there's different ways to get this, what we call delta G. Now, what does this delta G tells us? Okay, so the delta G would tells us that if you have a value that is less than zero, you have a spontaneous reaction. And if you have a delta G that is more than zeros, that is a non-spontaneous reaction. That's the criteria, but I'm going to what we call discuss this to you as we go on. Okay. Now, there are many reactions of this so-called delta G. So this is the one that connects your pre-Gibbs energy with enthalpy and entropy. But you can also have a delta G similar to what we call the delta H and the delta S. And this is what I call the Big Mama equation. Okay? So this is just the summation of the Gibbs free energy of the products minus the summation of Gibbs free energy of all the reactants. And what we're going to do, we're going to use the problem that we have earlier to determine delta G, both using the Big Mama equation and the Granddaddy equation. I just read this from some of other resources. Okay. So what did we get from the delta S here? Because it says here using standard enthalpies of formation, delta H, and the value of S from the previous problem, calculate the delta G. What's the delta S that we get from our previous calculation? Is that the negative what? Is that the negative 136 joule K per K, right?
Yeah.
Now let's try to get the K, the delta H value. So for this, the delta H is given as 2776.6. This one is 0. This is 467 or 487.0, and this is 285.8. So what would be the delta H that we can get here from this reaction? So all of them are 1 mole. So it's just negative 48.0 plus negative 285.8 minus negative 277.6 plus 0. So what's the answer that we can get here?
Negative 495.
Okay, so you get negative 495. Point
0.2.
0.2. Because I asked you to put the point, because remember, this is kilojoules. The one that's given here is in kilojoules, and the one that you have there is only joules. So you're going to use the granddaddy equation. And you need to replace this, or what we could convert this to kilojoules. So that's just become what? Right? So you're going to put the values here. So this is negative 495.2 minus, what's the temperature that we have here? That's a 298 times point negative 0.136 kilojoules per joules per K. So what do you get?
Negative 454.7.
Negative 454.7. So since this is a negative, that means it happened spontaneously. So those are the information that you need to know. First, the reaction is what? It's exothermic based on the delta H, right? It become more disordered based on the delta S, and last but not the least, it is spontaneous. So those are the information that you can get from this calculation. So the one that we have discussed here, the standard enthalpies of formation, okay, it's similar, most likely close to what? The enthalpy. Because the delta S, they don't have zero value. The only time the delta S is a zero value if it's in 0 Kelvin. So the standard free energy of formation is the free energy change that occurs when 1 mole of substance is formed from its elements in their standard states at 1 atmosphere and at a specified temperature, usually 25 degrees Celsius. And the corresponding reaction for the standard free energy of formation is the same as that for standard enthalpy of formation. So that's the one that I put as the big mama thing, like this. the products, the sum of the products minus the sum of the reactants. And the table that you have here is just like that. And as you could see here, there are zero values here. If you recall in your Gen Chem 1, okay, those are the zero values that you have. The form that they have at atmospheric pressure and 25 degrees Celsius. You don't see this in delta S, but you see this in delta H. So usually whatever zero in delta H, that's also zero in delta G. If you look at the previous discussion that we have here, so you see this one here, it's zero. So this is just, I would say, the Big Mama equation. And we're going to answer also the same question that we have here, but this time using, okay, the delta G of those elements that we have. And in theory, they should be what? They should be the same. So if we're going to calculate this value that we have here, so what I'm going to do is I'm going to put the number. So again, this is what? Delta G in kilojoules per mole. So this one has a value of 174.8. This one has 0, okay? Negative 392.5, and this one is negative 237.2. So what do you get? What's the delta G there? I'm not done. I'm not done yet. So what do you get?
Negative 454.9.
So compare it with what we have before. Negative 454.7. That's almost close, right? So whatever the value that you have, it's going to be close to that value. So question. Do you want to know now if gold is forever?
Yes.
So we're going to look at the value here. No, not gold, diamond, gold. So we have here what? Where is that? I already saw the pre-Gibbs energy of that. Carbon, 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 carbon. There.
Carbon dioxide.
So you have 2.99 and 0. So what does this mean? So we're going to look at the value that they have there. So you have here 2.9 for diamond and graphite 0. So what is the delta G? So how are we going to solve here? If that's the equation. So it will just be what? 0 minus 2.9, right? So that means what does this means? The negative 2.900. Is it spontaneous or not?
It's spontaneous.
So you would say it is spontaneous. So what is your answer now to the question? Are diamonds forever?
Yes.
What do you call this? In terms of thermodynamics or thermodynamically speaking, the answer is yes. But in terms of kinetics, the answer is no. I mean, no, I said, are diamonds forever? In terms of thermodynamics, the answer is no. In terms of kinetics, the answer is yes. So why did I say in terms of kinetics? In terms of kinetics is this one. So that means it will be converted to graphite. But in terms of kinetics, the answer is yes. Why? Because this process is so slow. The diamonds can last a lifetime. Okay? Because the process for the diamond to become graphite is a very slow process. But it will happen. But if you give somebody, okay, a diamond, or you can call it like what Gollum said, my precious, okay, it will last during that lifetime. But you can always say, oh, it will be converted to graphite. It's just, this is so expensive. And then graphite, what's the graphite that you know? The pencil lead. It's a cheap material, right? So that's the story that we have here in terms of this thing. And yeah, the diamond will turn into a pencil lead. So somebody give you a diamond. Oh, I will wait. Yeah, until this turns into a pencil lead, and that will be more than a lifetime. Okay, so I think I'll end the lecture for this year because the material is almost done. And after we're done with this, we go proceed with what we call with chapter 18. And this is the thing that I want to talk about you because we have a lot of time remaining. And unfortunately, I cannot change the schedule that we have because I am, we could say, beholden to my other colleague who is having this course. Now, what I'm thinking is maybe in one of those days before we have our uh, third exam, maybe one of those days I can ask you to take some sort of a makeup, whether it's the first or the second exam where you got low. But this only applies to those who have a score that is 80 and lower. Okay? So if you did 80 in both exams, you are not what we call, you don't have to worry about this thing. Okay? Because this is just for you to make up. Or maybe we can do it after your final exam. It's up to you because there will come a time that, because we put this schedule there, 2 meetings for nuclear reactions or nuclear chemistry, which we never did before. And as of now, as I've told you, we're almost done with chapter 18. So by next meeting, chapter 19 might be starting already. Okay? Your days are numbered already. Our days are numbered already in Chem 112. And I'm also calling my 112 lab, the Monday one. I want you to answer the question that I asked because the student lab assistance is waiting what she's going to prepare on Monday, whether it's just experiment 21 or half of experiment 22 is included, because I told you we might not meet on April 12th because I will have my second vaccine at the weekend there. So I just want to prepare for the worst. Okay? So I want you to do it because by at least I told you to do it by today, because I need to inform the student lab assistant she's going to prepare it by tomorrow, the reagents that she needs to prepare for Monday. So the option that you have there, I think I put the A, wherein you do 21 next week and then 22 and 23 on April 5, but there's two sets of students from the group. One will come around 9, the other one will come around 10:45. And the other options, which is B, wherein you're going to do this week 21 and half of 22, and then on April 5, half of 22 and 23. That's only for what we call my lab Monday class. So if you're not my lab students, that doesn't what we call includes you. Okay? So question. So that means I'm going to meet you only twice, my lab students. And April 12, if I'm going to feel well, we might meet online because we don't know. You heard the story. The second vaccine is worse. The second dose is worse than the first dose. So I'm preparing for that eventuality. Okay. So questions so far.